Hello, my name is Meriç.
And my name is Öykü.
And we will be presenting you our paper titled A Quantum Finite Automaton Framework for the Study of the Energy Complexity of Computations.
Our aim with this project is to generate an approach to study problems related to energy complexities of different types of finite automata, utilizing a modern quantum finite automata model. Also, we aim to come up with some answers to various problems we propose regarding energy complexities of finite automata. The most prominent one being whether or not we can build a zero-error quantum finite memory machine that is more efficient in terms of energy usage compared to its classical deterministic counterpart.
Let's start by introducing the concept of a deterministic finite automata. In the theory of computation, a DFA is regarded as the simplest machine to recognize and classify some patterns using a finite memory. It works by starting at the start state and following the execution according to each received letter. Then you accept the input string if the final state you end up at is an accept state, and reject if it is not an accept state. The DFA also can be represented as a vector and transition matrices for each character in our alphabet. The vector holds the current state as shown, and the transition matrices correspond to the arrows on the diagrams. So if you receive a character A, you multiply your state with that character's transition matrix to get your new state.
The probabilistic finite automata works similarly. The only difference is that the transition doesn't have to be deterministic. Therefore, the values inside the transition matrix doesn't have to be 1 or 0.
The earlier model introduced for a quantum version of the finite automata works similar to its classical counterparts. Only our states now act as a quantum state, and the values inside our transition matrices can be positive, negative, or even imaginary. The only constraint is that these matrices need to be unitary. However, this causes a problem. We would expect the quantum version of a machine to be more or even as powerful as its classical counterpart. However, since the transition matrices needs to be unitary, these machines can only recognize a subset of the languages recognized by DFAs, which is the set of reversible languages.
To overcome this problem, a variation on the quantum finite automata model was introduced. In this model, in addition to the main states, there are a set of quantum states called the auxiliary states, and a set of classical states that mimic these auxiliary states. Our conjoined set of quantum states become this. At the start of each computational step, instead of just multiplying with one transition matrix, we first multiply our state with the matrix that corresponds to our classical state, then the transition matrix of the character ref. After this operation, we observe our auxiliary state and set our classical state accordingly, which leaves us with a superposition of our main states.
The purpose of USI here is to rotate the auxiliary states back to the initial one. So if we have n main states, we only care about the first n columns of the transition matrix. The rest of the columns can be assigned to make the matrix unitary. We call this first n columns the super operator, and each n times n block an operation element.
Our state can also be represented as a density matrix, and the execution of one step is given in the figure.
This QFA model can also be used to represent any DFA or PFA as well. You only need to deconstruct the transition matrices of this finite automata so that each column inside our super operator is orthogonal. You can see that for reversible languages, since the transition matrices are unitary, the super operators are the same as the transition matrices itself.
Now, the question is how the energy complexity related to the model we are using. According to Landauer, raising a single bit of information requires at least the amount of energy shown here. As we remember, a quantum finite automata with n auxiliary states raises log n bits of information at each computational step when we set our classical state to the observed auxiliary state. That setting action makes us forget the state before by erasing that information, and that causes heat to dissipate to the environment. So n auxiliary states correspond to this amount of waste heat dissipated at each computational step.
Now, let's use the framework we constructed on a language. Let our alphabet consist of A and B, and let our language consist of words that end with B and contain BB as a substring. From an earlier paper of one of our writers, fruitful, we know that this language cannot have less than 3 auxiliary states. This corresponds to an energy cost per step of this.
The question we asked ourselves is that whether we can build a more efficient but still zero error finite automata by using quantum computation. We proved that this is not possible.
Think of any input that takes the DFA to the ith state. Then the vector space that is spanned by any possible quantum state that can be achieved with the same inputs is called SI. So there exists a vector space that corresponds to each state in our DFA. Here we have S1, S2, S3, and S4. Also, each of these vector spaces are spanned by a number of dimensions, D1, D2, D3, and D4. Firstly, we show in our paper that each of these vector spaces are orthogonal to each other.
Now assume that we have a quantum finite automata with 2 auxiliary states that recognizes this language. Imagine we have 3 different states, one in S2, one in S3, and one in S4. We know that all of these vectors are orthogonal to each other. And now imagine that we receive a character B while we're in one of these states. Since they are all multiplied by the same unitary matrix, their results are orthogonal as well. We know from earlier that the resulting matrices, before observing the auxiliary states, are n times m long, where n is the number of auxiliary states and m is the number of the main states. And since all of these resulting vectors need to be inside the vector space of S3, all of the results must coexist inside the vector space of n times B3 dimensions. We assume the auxiliary states count to be 2, so we have the following inequality.
We construct a similar inequation from the transitions shown by the color blue. But we see that these 2 inequalities introduce a contradiction if each vector space consists of at least 1 dimension. And they must if we want our QFA to be zero error.
So we conclude that the zero error QFA that recognizes this language needs to have at least 3 auxiliary states. This means we cannot construct a more efficient quantum machine compared to its classical counterpart.
What if we don't force our QFA to be zero error? Can we trade in determinism to build a more efficient finite automata? We constructed a QFA derived from this probabilistic finite automata shown here. You can verify by following the execution of this machine that it recognizes our language with an error of 1/3. Each superoperator for this finite automata has at most 2 auxiliary states, which correspond to a decrease in energy cost per step. So we showed that a more efficient finite automata can be achieved by allowing some error.
Thank you for your attention. You can reach us through our emails if you have any questions.